So good morning or good afternoon, depends when you are watching this video. This video is devoted to problem number 8, and the text of this problem is find reactions and calculate internal forces of a given frame on figure 16. Then you should plot diagrams of internal forces in a chosen scale. Check the equilibrium in given frame corners. In my case, we have frame with distributed load, with singular moment, and with two singular or concentrated forces. And our frame or my frame has one roller on the left and one hinge on the right. So first of all, we need to mark everything, so it is necessary give a names of points, so point A and point B for the supports, then see where the F1 is acting, D, E, F, G and H, for example, where F2 force is acting. And then it is very important also to depict the sign convention and the direction from which you are looking at your member. So it means for this column we are looking from the inside, the same for horizontal beam here, and for the right column it is the same, we are looking from the inside to outside. But it is not only the only one solution, you can also take a look from outside to inside, so it is really up to you. Then the second step is calculation of reactions, and it is not quite difficult, or it is not very different from previous assignments, so I will go very quickly through this calculation. So we have three different unknowns, three different reactions: AV at the roller and BV and BH at the support of hinge. For the calculation of these three reactions, it is fine to use, or it is recommended to use sum of forces in the horizontal direction is equal to 0. Then sum of bending moments around point B is equal to 0, because around this point is acting only one unknown as AV, and sum of moments around MA, so around point A is equal to 0. So 2 4 moments and one equation of equilibrium with forces. So here on this slide you can find the equations. Once again, for your information, it is necessary to have general equation or general expression. After that, it is necessary to have substitution with given numbers, and then the third step is that you have one result. So from this calculation we have BH. After that, sum of moments around point B, so this is expression. Then it is substituted with numbers, and according to that we can calculate AV. After that, sum of bending moments around point A. So you can find here we have PV times 4 and so on and so on. After that, substitution with given numbers and then the result. Next step is check of reactions. So for the calculation or for the check of reaction, we can use sum of forces in a vertical direction and sum of bending moments around point D, for example, but you can use also G, E, F, or C, or H. It is really up to you. So on this slide you can find all the values which are acting in vertical direction. So here we have only forces, and another calculation is sum of moments around point D. So you can find once again general expression, then substitution, and at the end we have the check. So the result is 1/1000 of kilonewton meter, so it is almost 0. After that we can continue with calculation of internal forces. So what we can do as the first step is to calculate values. We can try first of all the calculation of NDE from the left side, and it means that we are standing here, we are looking for this force because we are going from the left, and you can see that we have no force here. After that we can move from this section DE up to the section ED. So here we have E, and because of that here is the section ED. We can do a little bit like this, something like this. And now what we can see here, nothing, and because of that NDE and NED is the same value. For the next part we can start from the right side, so we can move this to the section GF. So this is GF section, so we can find GF here, and we are looking for this force from the right side, and you can see here, okay, we have here only bending moment, but we are looking for axial forces, so because of that it is 0. When we move to the section FG, so FG section is here, so it means this value, and you can see that still we have no force which is acting in center line or which is parallel to the center line of this beam. And the next step, we can go on to the left column, so we can move this sheet of paper and we can continue. So we are here at the section, we can write it here, NIC is equal to what? So we can now rotate our sign convention. we are calculating NIC from the left side. So from the left is this part, so we are looking for this force, and we can see now on the picture that AV is acting at that point, so we can write that it is equal to minus AAV. What will be change when we move to the section NCA? Nothing, because we still see only AV, so because of that it is minus AV. If we move to the NC and E, so this section here, the section here, NCE, from the left is equal still to AV. And if we move, okay, we can make it a little bit smaller, so we can put it like this, and we are now in the section EC, and everything which is on the right from this section is hidden, so because of that we have minus AV, or still minus AV. What next? NEF, so we can try to do the calculation on this horizontal part, so because of that we are here in this section, and this section is called EF, and we are trying to calculate it from the left side, and our task is to find all the values which are acting in the center line of this horizontal member or in the parallel way. So we are looking for this force, and between DE and nothing, but on the left column we have F1. This F1 is acting and not in center line, but it is the parallel force, so it should be minus F1, because the F1 is acting against the positive sign convention. So what next? We can continue with the calculation of these axial forces. It means it is from the right side, so we are looking for this force, axial force in positive direction. So it means that in this section we have minus BV because it is acting against, so we can move this, and we can also rotate this, so it is like this, and from the right we have this direction, so because of that it is minus BV. When we move to the BH, HB is still the same, and also NFB is the same value of minus BV. Now we can continue with shear forces, but the way how to do it is almost the same like for the axial forces. So we can use this sheet of paper or some auxiliary part which is used for the hiding of part of structure. So And once again, we can start at the section DE. So you can see on the right that VDE from the left side is equal to 0 because nothing is acting from the left in this direction. When we move, when we move to the section ED, so ED is here, and ED is this section, so I'm talking about this section. Once again, it is from the left side, and what we can see here is minus q times 1.5. Then we can continue with the right part, right cantilever. So we can write that VGF from the right is the same like VFGY. So here is nothing which is acting perpendicularly to centerline, but only bending moment. But we are looking for shear forces, and you can see that we have no shear forces when we move from GF to FG. So because of that, it is 0 kilonewtons. Then we can continue with another section, and section can be VAC, so shear force at the section AC. So I'm talking about this section, and what we can see is that in that section we have nothing which is acting perpendicularly to centerline, and because of that VAC and VCA is equal to 0. So VAC, VCA, but after we go through the section or to the section CE, we can find this force, and because of that the next value VCE is minus F1, because of that minus 12 kilonewtons. VFE, so what we have here, or we can continue with VEF. So we are talking about this section. So here we have VEF, and what we are looking for. So from the left side, the shear force is acting from the bottom part to the top part of this slide, and because of that we can see on this slide AV with the positive sign and minus Q times 1.5, sorry, which is acting in negative direction. So this is VEF from the left once again. And what else? We can calculate also VFE from the right side, and it is only BV because we are looking for this value or these forces in this direction, but you can see that only BV is acting in similar way, but the direction is opposite. When we would like to calculate value of BH or HB, so you can see that is only BH, and when we move to the shear force HF, we can find also BH minus F2. And once again, it is from the right. It is from the right. So the same is for the bending moment. So according to this auxiliary piece of paper or auxiliary rectangle, you can go through all the sections what you need. So something like this. So MDE, from the left we have 0 because nothing is acting around this section. When we move to the ED, so we have here, so it is minus Q times 1.5 times 1.5 divided by 2. So this distance here is multiplied by this distance divided by 2. And because of that, here we have the distributed load. It is necessary to calculate also the point in the middle. So for example MED, so, and the point in the middle is this value. After that you could move with this piece of paper through all the sections. So GF, so we can hide a structure like this, so we can see that only bending moment in opposite direction is there, so minus 16 without any change to FG section. So because of that we have minus M. Then we can continue with MA, so it is 0 once again. MAC is the same like MCA, so it is 0, so we can use also this AC and CA. It is 0 because nothing is acting there, and MC CE is 0, 2 MCE, but MEC from the left, everything from the left, is equal to minus F1 times 1.5. The same you can do with another values of bending moments. So I will go on, and we can, or we should find the calculation of extreme. So from the left side it is written like this, and according to that we can find that extreme value of bending moments is in the place of XE 1.845, and bending moment is calculated then according to this calculation, and the value is minus 3.5 kilonewton meters. What is also important is to check of equilibrium in the frame corner. So here you can find the frame corner, so our node, and here we have the element with sign convention, and also here is element with sign convention. So first of all it is necessary to plot this frame corner, then the mark of E. After that you should plot the sign conventions. So you can see here that here we have the axial force, here we have the shear forces, and once again shear forces, and the right direction is according to the sign convention, and the force which is acting in the corner is in the opposite direction as we have on sign convention. So you can see that these two forces are are equal to 0. Once again, these two forces are equal to 0, and also these two, and so on and so on. And after that, you can write that for node E, we have the sum of forces in vertical direction. So NEC is here, VEF is here, and VED is here. So after the substitution, so once again general substitution, and according to that you can say that 0 is equal to 0. What about horizontal forces? So you can find horizontal forces here. So here is the element, here is the element 2, and according to these pictures you can calculate that VEC minus NEF is equal to 0 after substitution, and we can say that 0 is equal to 0. And the same is or can be applied on the node F. So what about check of equilibrium in frame corner when we have the bending moment? So once again it is necessary to plot the node with the corner of members. Then it is necessary to plot the member with sign convention. So this is the member with sign convention, once again here and here, and according to that these two moments must be equal to 0, these two moments must be equal to 0, and here is the moment from the cantilever beam, so these two moments must be in equilibrium. After that, the directions of bending moments are correctly drawn in our picture, and then we can write that the equation is equal to 0, so MEC plus MED minus MEF is equal to 0. After substitution we can say that 0 is equal to 0. On the next slide we have the diagrams of axial forces, shear forces, and about shear forces we must draw the bending moments. One note is here that plus, minus, plus, minus, but for bending moments you can find that the negative values are drawn on the top part of the member, and positive are at the bottom part. So it is different from axial forces and shear forces, so please be careful about that, and please prepare it according to that. So what about summary? Text of the problem, name the scheme, diagrams of internal forces, calculation of extreme value, and here we have the proof of equilibrium in a frame corner. So only one corner when three members are connected. So for me it's this corner and this corner, and it was already done. So thank you for your attention, and see you on lecture or seminar. Goodbye.